Welcome back. Let's learn about lines in 3D space. Alright, so in two dimensions, or in a plane, in order to find the equation of a line, we needed to know at least one point on that line as well as the slope of that line. And you could find the slope of a line using 2 points, which you can see that I have labeled on this line here. We have 2 points, P1 and P2, where P1 has coordinates x1, y1, and P2 has coordinates x2, y2, we could use these 2 points to find the slope of this line, and then use one of those points and that slope to find the equation of this line. And so that looks like this. Remember from algebra, that slope is equal to rise over run, or the difference in the y-coordinates divided by the difference in the x-coordinates. And then using that slope and one of those points, we can use the point-slope formula to find the equation of the line, or we could also use the slope-intercept form of the equation of a line, which maybe you're more familiar with, y equals mx plus b. Alright, so this is nothing new. You learned about this in algebra and have been working with it ever since, but now what we want to do is extend this idea of writing the equation of a line into the third dimension, right? We're no longer working with a line in a plane, now we're looking at a line in 3D space. How do we find the equation of this line? What things are we going to need in order to find the equation of a line in 3D space? Well, for one thing, similar to a line in 2D, we're going to need to know a point on this line. All right, that's the first thing that we need to know. And so that can be any point along this line. And so for example, I'm just going to pick a point right here and label it as P1. And that's going to have the coordinates of x1, y1, and z1. And then along with that point, instead of needing a slope like we do in 2 dimensions, what we are going to want instead is a vector. In particular, a vector we call a direction vector, a vector that describes the direction of this line. And so essentially what that means is that that direction vector will be parallel to this line, okay? And so that vector might look something like this. That could be vector v, a direction vector that describes the direction of this line. It's parallel to that line. And so those are the only 2 things that we are going to need to write the equation of a line in 3D, or to represent a line in 3D space. Okay, so in 2D we needed a point and a slope, but in 3D we're going to need a point and a direction vector. Okay, so those are the 2 things that we need to have in order to find the equation of a line in 3D, but how do we actually find that equation? Well, that is what we're going to look at next. Alright, so if we want to find the equation of this line using a point on that line and a direction vector, the first thing that we need to make a note of here is the fact that the direction vector and the line are parallel. I mentioned this earlier, but because this direction vector is describing the direction of the line and that direction vector must be parallel. They have the same direction. Okay, so that's the first thing that we want to write down here. We know that that line is parallel to the direction vector, vector v. All right, and I just want to point out here that that direction vector does not necessarily need to be a unit vector. I know we typically associate unit vectors with direction, but in this case, this direction vector does not need to be a unit vector. It can be a unit vector, but it doesn't have to be. All we need in order to represent the equation of a line in 3D is a vector that is parallel to that line. Okay, but now as a result of this statement, the fact that the line is parallel to the direction vector tells us something else about that line. If we were to represent the line with another vector, what that would tell us is that the vector for that line and the direction vector would also be parallel, which means that they would be scalar multiples of each other. And so if we were to represent the line with a vector, I'm just going to write it like this. I'm going to write vector sub L, or a vector representing the line. That would be a scalar multiple of vector v. And we can define that like this. We can write some scalar value, which I will represent with t, and multiply it by vector v, the direction vector. All right, remember when vectors are scalar multiples, that just means that one vector is equal to the other vector multiplied by some scalar value. You could have chosen any letter you wanted to represent that scalar, but I did choose t here for a very specific reason, which you will see later on. But keeping this in mind, what we want to do now is define what each of these vectors would be equal to. Okay, and let's start with the vector representing our line, or a vector along this line. What is another way that we could define that vector? Well, remember, we can find a vector using any 2 points. We can connect 2 points and create a vector. So if we want to define a vector along this line, what we should do is use this specified point right here, P1, and then any other point along that line, and we can create a vector. All right, and so using that specified point P1, which has coordinates x1, y1, and z1, and any other point on that line, which I'm going to represent with just a generic point P with coordinates x, y, and z, which is a point on the line, we could create a vector between those 2 points that would be along this line. All right, we would choose P1 to be our initial point, and then that point P to be our terminal point, which would be some other point along this line. All right, so we're going to define that vector sub L to be equal to the vector P1P, the vector that starts at point P1 and ends at point P. All right, and then we could actually find the components of that vector using the coordinates of point P1 and point P. We can subtract the coordinates of the initial point P1 from the coordinates of the terminal point P. And so we would have x minus x1 for the x component, then y minus y1 for the y component, and then z minus z1 for the z component. And so that vector would look like this. We would have x minus x1, y minus y1, and z minus z1. And so now what we have here are the components of a vector that would lie along line L. All right, so now we've defined what that vector is, but what about the direction vector, vector v? Well, here's how we define that vector. Vector v will be equal to some vector with an x component of a y component of b, and a z component of c. All right, and these 3 components actually have a special name. We refer to them as direction numbers. They are the numbers that are going to describe the direction of our line. And so those direction numbers are going to define that direction vector. And so now that we have defined this direction vector, vector v, and we have defined the vector lying along that line, we can rewrite this equation right here. Since we know that a vector lying along line L would be a scalar multiple of vector v, we could say that vector P1P is a scalar multiple of vector v, right? So we would have that vector P1P is equal to that scalar multiple of t multiplied by vector v. We're continuing this equation right here. But now what we want to do is actually rewrite these 2 vectors with what they're actually equal to using their component forms, right? So if we do that, we'll have a vector with components x minus x1, y minus y1, and z minus z1 is equal to that scalar multiple of t multiplied by vector v, the direction vector, which has components of a, b, and c. All right. And now what we want to do next is perform scalar multiplication between t and this vector. We want to multiply t by each of those components. And if we do that, we'll have this vector, which I'm just going to rewrite really quickly here. That will be equal to a vector where the x component is a times t, the y component is b times t, and the z component is c times t. Okay, and so now we have performed this scalar multiplication. We multiplied t by each of those components right here. And so now what we have here is an equation where we have 2 vectors equal to each other. And so if we're saying that these 2 vectors are equal, right, this is vector p1p, and this is vector v multiplied by some scalar t, if we're saying that those 2 vectors are equal, then what that really says is that all of their components are equal, right? This is one of the first things that we talked about early on in Calculus 3 when we first introduced vectors, If two vectors are equal, what that means is that their components are equal. Their x components must be equal, their y components must be equal, and their z components must be equal. So if we know that these two vectors are equal, we can set up a few equations by setting the x, y, and z components equal to each other. And so if we do that, here's what we'll have. We'll have x minus x1 is equal to a times t, and then we'll have y minus y1 is equal to b times t, and then we'll have z minus z1 is equal to c times t. Okay, and then if we solve for x, y, and z in these three equations, we're going to come up with a very interesting result. All right, and so let's do that. In each case, in order to solve for x, y, and z, we just need to add x1 to both sides of the equation, y1 to both sides of the equation, and z1 to both sides of the equation. And so if we do that, we'll have that x is equal to a times t plus x1, and then we'll have y is equal to b times t plus y1, and then we'll have that z is equal to c times t plus z1. Okay, and now what we have here with these three equations is a set of parametric equations that will represent a line in 3D. All right, we can use these three equations right here to represent a line in 3D space. Using a specified point along that line and a direction vector that is parallel to that line, we can use the coordinates of that point and the direction numbers from that vector to set up these three equations that will represent this line. All right, and for these parametric equations, the parameter is t, and so now maybe it makes more sense why we let t be our scalar multiple. Now everything has come full circle. The reason we chose t is because typically we use t as our parameter in a set of parametric equations. And if you're not familiar with parametric equations, you do learn about them in calculus 2. So if you need a quick refresher, feel free to go back and watch my lesson on parametric equations. But that is exactly what we have right here, except now in 3D, of course. We have three different equations that together make up a set of parametric equations that represent this line. We can choose a value of t to plug into these equations, and we will get a respective x, y, and z coordinate that will make up a point on that line. All right, and so you could choose a bunch of different values of t to plug in here, get a whole bunch of points that you could then plot in the 3D coordinate system, connect all those points, and create a line. Okay, and so these are the parametric equations of a line in 3D, but there's actually another way for us to represent a line in 3D, which we can find by manipulating these parametric equations a little bit. And so let me show you that next. What we're going to do here is solve for that parameter of t in each of these parametric equations. So the first step to doing that is to subtract x1 from both sides of this equation, subtract y1 from both sides of this equation, and subtract z1 from both sides of this equation. So if we do that, we'll have x minus x1 is equal to a times t, and then y minus y1 is equal to b times t, and then z minus z1 is equal to c times t. All right, and then for each one of these equations to solve for t, we just have to divide both sides of each equation by their respective direction numbers, a, b, and c. And so if we do that, we'll have x minus x1 divided by a is equal to t, and then we'll have y minus y1 divided by b is equal to t, and then z minus z1 divided by c is equal to t. Okay, and so now for each of these parametric equations, we have some expression involving the coordinates of our specific point on the line and the direction numbers from the direction vector, and they're all equal to that parameter of t, and so what we can do is set up something called a symmetric equation. Since they're all equal to t, then each of these expressions must be equal to each other. So we can write this, we can say that x minus x1 divided by a will be equal to y minus y1 divided by b, and that will be equal to z minus z1 divided by c. Since all three of those expressions are equal to that parameter of t, we can set them all equal to each other. And what we're left with is the second way to represent a line in 3D. This is known as the symmetric equation of a line in 3D. Okay, so it took us a while to get to this point, but these are the two different ways, or the two different types of equations that we can set up to represent lines in 3D. All right, and so now in both cases, you can see that what we said at the beginning of this lesson is true. To find the equation of a line in 3D, you need a point along that line, and you need a direction vector. You use the coordinates of that point and the direction numbers of that vector to set up each of these equations. Okay, so to summarize, to find the equations of lines in 3D space, you need to know a point P1 on that line with coordinates x1, y1, z1, and a direction vector, vector v, with components or direction numbers a, b, and c, and then use those components and those coordinates to either set up a symmetric equation of a line in space that looks like this: x minus x1 divided by a is equal to y minus y1 divided by b, which is equal to z minus z1 divided by c, or you could set up a set of parametric equations of a line in space, which look like this: x is equal to a times t, the parameter, plus x1, and then y is equal to b times t plus y1, and then z is equal to c times t plus z1. Okay, and so now that you've seen how we represent lines in 3D space, let's actually take a look at some examples where we set up these symmetric and parametric equations. All right, so here's our first example. We want to find a set of parametric equations and a symmetric equation of the line passing through this point, which is the origin, the point 0, 0, 0, and is parallel to the vector v, which is the position vector of the point 3, 1, 5. Okay, and so in this problem, we are given everything that we need to set up some parametric equations and a symmetric equation to represent this line. Remember, to represent a line in 3D space, we need a point on that line. That would be this point right here. The line passes through this point of 0, 0, 0, and we need a direction vector, or a vector that is parallel to that line. And that is exactly what we're given right here. We're told that the line is parallel to this vector, vector v. So vector v is the direction vector for our line. So we have both things that we need. We have a point and we have a direction vector, so all we have to do here is identify each of those coordinate values and each of these direction numbers, and we can set up our parametric equations and symmetric equation of the line. Okay, and so for the first example, I have the general form of those equations right here for us to reference, but going forward, it's going to be a good idea for you to sort of memorize these, and that'll kind of come with time. As you do more and more of these examples, you'll start to just naturally remember these equations. They're not too complicated, so if it seems a little overwhelming right now, don't worry. The more you work with these equations, the better that you will remember them. Okay, and so let's get started here. The first thing that I want to do before I try to write out any of these equations, though, is identify the direction numbers. Okay, one of the worst things that you can do in these problems is reverse the placements of the direction numbers and the coordinates of your point. All right, x1, y1, and z1 are the coordinates of the point that the line passes through, while a, b, and c are the direction numbers or the components of the direction vector. All right, so you don't want to mess that up. You want to make sure that you identify those numbers correctly. Okay, so if we look at our direction vector here, the x component is 3, the y component is 1, and the z component is 5. So that means that a is equal to 3, b is equal to 1, and c is equal to 5. Okay, so hopefully by writing that down explicitly, that will help you not make the mistake of putting the wrong numbers in the wrong places in these formulas. Okay, but now let's start with the symmetric equation. We're going to have x minus x1, which is the x coordinate of the point, which is 0. And notice that all three of these coordinates are 0. So y1 is 0 and z1 is 0. That makes this pretty easy. We're going to have x minus 0 divided by a, the x component of our direction vector, which is 3. All right, so we're dividing by 3. And then that will be equal to y minus y1, which is 0, and then we will divide by the direction number of b, which is 1. That's our y component of the direction vector. So we're dividing by 1. and then that will be equal to z minus z1, which is also 0, and then we divide by c, that direction number, which is 5, the z component of the direction vector. So we divide by 5, and now if we simplify, x minus 0 is x divided by 3 will be x divided by 3. So we have x divided by 3 is equal to y minus 0, which is y, divided by 1, which is also y. So we'll just have y, and then that will be equal to z minus 0 divided by 5. And z minus 0 is z, so we'll have z divided by 5. Okay, so I'll write z divided by 5, and that right there is the symmetric equation for the line passing through this point, and that is parallel to this vector. All right, and so that's one way that we could represent that line, but we could also represent it using a set of parametric equations. So let's set those up next. We're going to have x is equal to a times t, so we have 3 times t plus x1. All right, and once again, x1, y1, and z1 are all 0 in this case. So for each of these parametric equations, we're just going to have x equal to a times t, y equal to b times t, and z equal to c times t. So we'll have x is equal to 3t, and then if you want to write it down, you could write plus 0, and then we'll have y is equal to b times t, so we have 1 times t plus 0, and then for z, that will be equal to c times t, which is 5, and so we have 5t plus 0. And so then if we simplify, we'll have x is equal to 3t, comma, y is equal to t, and z is equal to 5t, right? Y would just be equal to t because 1 times t is t, okay? And so that right there would be the set of parametric equations that would represent the line in this example. Whenever the given point that your line passes through is the origin, these problems are pretty simple because x1, y1, and z1 are all 0, which makes for some nice, simple equations. And so that's it for this example, but let's take a look at another one where our point is not as nice. All right, so here's our second example. We have the same directions as the previous example, except we have a different point that our line passes through, and we have a different vector that the line is parallel to. Okay, but now I'm just going to read through it real quick, just so you get an idea of what we're doing once again. We want to find a set of parametric equations and a symmetric equation of the line passing through this point of 7, -2, 6, and is parallel to the vector u, which is the position vector of the point 4, 3, -1. Okay, so just like the previous example, we have everything we need here to represent this line in 3D space. We have a point on that line, and we have a vector that the line is parallel to. In other words, we have a direction vector. And so let's get started here. You'll notice that I don't have the general form of our equations here for us to reference. That's because I want you to get used to trying to write these from scratch. Like I said earlier, you'll begin to sort of memorize these naturally as you work with them more often, but they're not too hard to remember. Let's start with the symmetric equation. I always like to start with that. And so we'll start with the first part of the symmetric equation. We'll have x minus x1, which is the x coordinate of our point, which is 7. So we have x minus 7 divided by a direction number a, or the x component of our vector. In fact, let's write those down. Let's write down our direction numbers. I forgot to do that first. You should always write those down so that you're less likely to make a mistake later on. We know that a is equal to 4, b is equal to 3, and c is equal to -1. Those are the direction numbers from our direction vector. The x component is a, the y component is b, and the z component is c. But now that we have those written down, let's divide x minus 7 by a, which is 4. So we have x minus 7 divided by 4, and that will be equal to y minus y1, or the y coordinate of our point, which is -2. So we have y minus -2, and then we're dividing by the direction number b, which is 3, or in other words, the y component of the direction vector. So we're dividing by 3, and then that will be equal to z minus z1, which is the z coordinate of our point, which is 6. So we have z minus 6 divided by the direction number c, which is -1. That's the z component of our direction vector. So we'll divide by -1, and now if we simplify, There's nothing to really change for this part, so we're just going to have x minus 7 divided by 4, but then that will be equal to y minus negative 2 divided by 3. Y minus negative 2 will become y plus 2, so we have y plus 2 divided by 3, and then that will be equal to z minus 6 divided by negative 1. Now, if you wanted to, you could divide both of these values by negative 1, and so you'd have positive 6 and negative z. But for a symmetric equation, you don't really have to do that. I'm just going to leave it in this form. I think it's easier to look at it in that way. That way we can easily identify that direction number of c. So I'm just going to write it like this. We'll have z minus 6 divided by negative 1. Okay? And so that right there would be the symmetric equation for this line passing through this point and being parallel to this vector. But now let's find a set of parametric equations. Remember that for the parametric equations, we're going to have x equal to a times t, and then we're adding x1, and then we follow that same format for y and z, except we use their corresponding direction number and coordinate from the point. All right, so let's start with x here. We're going to have 4 times t, so we'll have 4 times t, and then we're adding the x coordinate from our point, which is 7. So we have 4t plus 7. Then for y, we will have b times t. All right, so we have 3 times t, and then we're adding the y coordinate, which is negative 2. So we have negative 2. And then for z, that will be equal to c times t. So we have negative 1 times t. So I'll write negative 1 times t, and then we're adding the z coordinate, which is 6. So we have 6. Okay, and so now if we simplify, we'll have x is equal to 4t plus 7, y is equal to 3t minus 2, right? 3t plus negative 2 is the same as 3t minus 2, and then we'll have z is equal to negative t plus 6. All right, negative 1 times t is just going to be negative t. And so there you have it. That is a set of parametric equations that would represent the line passing through this point and is parallel to this vector. All right, and I don't think I mentioned this earlier, but something to take a note of here is that this set of parametric equations is just a set of parametric equations that would represent this line. It is not the set of parametric equations, all right? There is not just one correct answer to these problems. This is the set of parametric equations that makes the most sense to find based off the vector that we were given, right? This is the vector that we're told our line is parallel to, but we could use any other vector that is a scalar multiple of vector u, and we would still have a direction vector parallel to the line, right? Because scalar multiples of vectors are parallel to each other, so you could multiply this vector u by a scalar multiple of 2 or 3 or 1/2, and that vector would still be parallel to the line, and so you could still use that vector to find a set of parametric equations. But then, of course, the parametric equations would look a little bit different because the direction numbers would also be different. And in a similar way, the point that we use to create the parametric equations could be different as well, because you can use any point on the line to represent it. But in these problems, we are restricted to using a specific point, the point that we've been given, because we have no other way to get another point on that line until we have a set of parametric equations. All right, I hope that's not too confusing, but I just wanted to explain why we are finding a set of parametric equations and not the set. There is not just one answer to these problems. There are an infinite number of correct solutions depending on the direction vector and point on the line that you use. And of course, all of that would apply to the symmetric equation as well. Okay, but with that, that's it for this example. Let's take a look at a slightly different one. Okay, so for this example, we want to find the coordinates of a point on the line and a vector parallel to the line. And so we're given a line here. In particular, we're given a set of parametric equations that represent a line in 3D space. Okay, so this is kind of the opposite of what we've been doing so far. This is the reverse of the previous two examples. Instead of finding a line using a point and a direction vector, we want to find the point and the vector using the line. All right, and this is actually way more easy than it might seem at first. All you have to do is remember what makes up these parametric equations. We just need to reverse that process of what we've done before. All right, and so remember the general form of these parametric equations. X would be equal to a times t plus x1, then y is equal to b times t plus y1, and z is equal to c times t plus z1, okay? And so remember, the direction numbers make up the components of a direction vector, the vector that would be parallel to this line, and x1, y1, and z1 make up the coordinates of a point that would be on this line. So hopefully you can see that this is a pretty easy process. A is going to be equal to the coefficient of t for x, which is 4. B is going to be equal to the coefficient of t for y, which is -2. And c is going to be equal to the coefficient of t for z, which is 1. And then whatever value is being added to that t term will be the corresponding x, y, and z coordinates. So here's what we find. Our vector, our direction vector, I should say, is going to have the components of 4, -2, and 1. All right, those are the three direction numbers, a, b, and c, from these parametric equations. Now for the point, our point P is going to have an x-coordinate of 8, that's what's being added to 4t, a y-coordinate of 3, that's what's being added to -2t, and then a z-coordinate of 0, because nothing is being added to this t, right? You can imagine that we would have plus 0 for that equation. So our point will be 8, 3, 0. And that's it. That is the solution to this example. We just reversed that process that we did in the previous two examples and found a vector parallel to our line and a point on that line using its parametric equations. Okay, let's take a look at another example. Next up, we want to do the same thing that we did in the previous example. We want to find the coordinates of a point on the line and a vector parallel to the line that we have right here. All right, so once again, we are reversing the process that we had done before, but now the line that we're working with is in symmetric form. We have a symmetric equation of this line in 3D space. And personally, I find these equations easier to work with. I think that this type of problem is much easier with a symmetric equation because your direction numbers are just going to be the numbers in the denominator of each part of that equation. 2 is going to be the direction number of A, 4 is the direction number B, and 5 is the direction number C. Okay? And then in the same way, whatever number is being subtracted from x, y, and z, that will be the x, y, and z coordinates of a point on this line. Because if you remember the general form of the symmetric equation of a line in 3D, it's x minus x1 divided by a, and that's equal to y minus y1 divided by b, which is equal to z minus z1 divided by c. And so x1 will be 9, y1 will be 0 because we have y and that's it, so y minus 0 would be y, so y1 is 0, and then z1 would be -2, right? We have z plus 2, but the general form is z minus some number, and so z minus -2 would be z plus 2. Okay, and so what we learn here is that our direction vector, vector v, will be the vector with components 2, 4, and 5, and then a point on the line will be 9, 0, -2. Okay, that is a solution to this example. We found a direction vector from this line that would be parallel to the line, and we found a point that would be on that line as well. All right, as long as you remember the general form of a line in both symmetric and parametric forms, these problems are not too bad. Okay, now before we look at another example, I want to briefly talk about a side note regarding what happens to your line when one of your direction numbers is 0. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, so sometimes you will get a line where the vector that it's parallel to has a component that is 0. Or in other words, one of the direction numbers is equal to 0. So that could be A, B, or C. If one of those direction numbers is 0, what's going to happen is that the line you were trying to represent is a line that is in a specific plane that we can determine pretty easily. And so let me break it down for you. This is kind of how it works. If A is equal to 0, that would be the x component of your direction vector. Then for your parametric equation for x, you're going to have x is equal to 0 times t, right? You would have a times t plus x1. And so you have 0 times t plus x1, which means that this whole term just becomes 0. Anything times 0 is 0. So this equation just becomes x equals x1. And that on its own is the equation of a plane, right? In the 3D coordinate system, if you have x, y, or z equal to just some number, that represents a plane in the 3D coordinate system. And so if x equals x1 is one of the equations in a set of parametric equations for a line, that means that your line will be contained within this plane, which is a plane parallel to the yz plane. All right, so here's kind of what that looks like. This would be a plane that crosses through that x value of x1. The line parallel to a vector with an x component of 0 is going to be contained within this plane. So that could look something like this. There's a lot of different possibilities here, but that could be the line that we're referring to. It would just be contained within that plane. For points along this line, the z and y coordinates can be anything, but the x coordinate will always be some value x1. And so because of that, this line will never leave this specific plane, x equals x1, in a 3D coordinate system. The line will always be contained within that plane if a equals 0. All right, now in the same way, if b equals 0, meaning the y component of your direction vector is 0, then the equation for y from a set of parametric equations for your line will look like this. You'll have y is equal to 0 times t plus y1. That term will become 0, so you just have y equals y1, which means that your line will be contained within this plane, the plane y equals y1, which would be a plane parallel to the xz plane. And so if this value right here is y1, this would be a plane that crosses through that value of y1. The line parallel to the vector with a y component of 0 will be contained within this plane. All right, so your line might look something like this. It could be any line really, as long as it's inside that plane. But the point is, if y equals y1 is your parametric equation for y in a set of parametric equations for your line, then your line will be contained within that plane. For all of the points on that line, the y coordinate will always be y1, so you're not going to have a different y value for any of those points. You're always going to be within that plane. Okay, your x and z coordinates can be different. They can be any value they want to be, but your y coordinate will always be y1. Okay, and then finally, in the same way, if c equals 0, if the z component of your direction vector is 0, then the parametric equation for z will look like this. Z will be equal to 0 times t plus z1. This term will become 0, and so you just have z is equal to z1, which would represent a plane parallel to the xy plane. And so essentially what's going on here is if you have a line parallel to a vector where the z component is 0, that line will be contained within the plane z equals z1. All right, so that line could look something like this. Again, there are a lot of different ways that that line could look, but the main idea is that it would be contained within this plane that crosses through that value of z1. The x and y coordinates of points along this line can be anything, but the z coordinate will always be z1. Okay, and so your line will be stuck in that plane, z equals z1, and therefore will be parallel to the xy plane. Okay, and so I hope this was a helpful visual for you of what happens to lines in 3D space when each of those direction numbers are equal to 0 for your direction vector. It's not particularly common, but you will definitely come across lines where this will happen at some point or another. And so with that, let's take a look at a quick example where we actually have a direction vector where one of the components is 0. Here's our example. We want to find a set of parametric equations and a symmetric equation of the line passing through this point of 1, 1, 1 and is parallel to the vector A, which is the position vector of the point 2, 2, 0. And so as you can see, the z component is 0, which would be the direction number c, and so one of those direction numbers is 0. And so let's work on finding each of these equations. I always like to start with the symmetric equation, and so let's work on that. But first, let me just quickly write down what each of our direction numbers are. A is going to be 2, B is going to be 2, and C is going to be 0. So A equals 2, B equals 2, and C equals 0. All right, now for our symmetric equation, we're going to have x minus x1, the x coordinate of our point, which is 1. In fact, notice that all 3 coordinates are 1, so that makes things pretty simple here. We're going to have x minus 1 divided by a, which is 2, and then that will be equal to y minus y1, which is 1, divided by b, which is also 2, and then that will be equal to z minus z1, which is also 1, divided by c, which is 0. And if you're thinking that that's a problem, it is, right? We typically don't like to have 0 in a denominator. We can't divide by 0. That is not a defined value. And so this is a little bit problematic. We're going to have to make some type of adjustment to this symmetric equation. We can't leave it in this form. That would not be a proper way to define the line here. And so we'll come back to this. We'll talk about how to adjust this in just a second. But first, let's just find our parametric equations because that's actually what's going to help us figure out how to adjust this symmetric equation. Okay, so for a parametric equation, we're going to have x equal to a times t, and a is equal to 2. So we'll have 2 times t, but then we want to add the x coordinate from our point, which is 1. Then for y, we will have b times t, so we'll have 2 times t, and then we add the y coordinate, which is also 1, and then we have z is equal to c times t, so we're going to have 0 times t plus the z coordinate, which is 1. All right, and so now if you've been following along throughout this entire video, you might recognize what we have right here from that side note that I just spent some time on. Notice that we have z equal to 0 times t plus 1, or 0 times t plus z1, where z1 is equal to 1, this term will become 0. Anything times 0 is 0, so this just becomes 0, so we have z equals 0 plus 1, which is 1, so we have z equals 1 as the parametric equation for z. That's going to represent our line. Now if I just rewrite these other two parametric equations here, we have x equals 2t plus 1 and y equals 2t plus 1. Together, those three equations make up a set of parametric equations that would represent this line, but notice that z is equal to 1 does not involve that parameter of t at all. Z is always going to be equal to 1, no matter what value of t you plug in to get an ordered triple of an x, y, and z coordinate for a point on your line. You're always going to end up with 1 for that z coordinate. Every single point on this line, in this example, is going to have a z-coordinate of 1. And because of that, that means that the line will be contained within the plane z equals 1. If I were to draw a rough sketch of the 3D coordinate system, if this is the z-axis here, and then this is the y and the x, if this is z equals 1, our line in this example would be contained within the plane that would cross through that value of z equals 1. The line is going to be parallel to the x, y plane. Okay, so that's what's going on here with this line. But now, how do we adjust the symmetric equation to account for the fact that we can't divide by 0, right? This is a problem. Like I said earlier, you can't leave it like this. We have to adjust it. And so the adjustment is actually pretty simple. All we do is just remove this last part of the symmetric equation, and then we just write comma z equals 1. That last part of our set of parametric equations. Since z equals 1 doesn't contain t, it doesn't have that parameter, we can just tack that on to the end of our symmetric equation. So we have the two parts that are not problematic, and then we just have comma z equals 1. Okay, and so that would be how we would represent the symmetric equation of this line that is parallel to a direction vector where one of those direction numbers is 0. All right, so here's our last example. We want to show that the two lines are parallel, and we have two lines given to us here, L1 and L2. Both are given to us in symmetric form. We have symmetric equations for these lines, and we want to determine if they are parallel. And so how do we do that, right? What does it mean for two lines to be parallel? Well, in 2 dimensions, if you remember, 2 lines were parallel if they had the same slope. Well, what about lines in 3 dimensions? How do we know if they are parallel? Well, that is going to be based on their direction vectors. And so here's what you need to know. Like I mentioned, lines are parallel in 2D if their slopes are equal, but in 3D, lines are parallel if their direction vectors are parallel. In other words, if their direction vectors are scalar multiples of each other. And the reason why that makes sense is because the direction of lines in the 3D coordinate system are determined by their direction vectors. The direction vector of a line describes its direction. So if 2 lines have direction vectors that are parallel, then those lines must also be parallel, okay? And we know that parallel vectors are scalar multiples of each other, which just means that one vector is equal to another vector times some scalar value. And so if we want to check to see if 2 lines are parallel in a 3D coordinate system, we just have to find their direction vectors and see if they're scalar multiples. So let's do that for this example. Remember that the direction vectors for each line are composed of their direction numbers, which are the values in the denominator of each part of the symmetric equations. So we can very quickly find these direction vectors. The direction vector v1 for the line L1 will be equal to 3, 7, 6, right? That is just these direction numbers. 3 is A, 7 is B, and 6 is C. So that's the direction vector for this line. Then for line 2, or L2, we'll have a direction vector v2, which will be equal to the position vector of the point 6, 14, 12. Right? Those are the direction numbers for line 2. And so now, if we compare these 2 vectors, can we determine if they are scalar multiples? Well, if you look at vector v2 here, if we pull out a common factor of 2 from each of these components, notice that they're all divisible by 2, they're all even numbers, what we'll find is that this is equal to 2 times the position vector of the point 3, 7, 6. Right? 6 divided by 2 is 3, 14 divided by 2 is 7, and 12 divided by 2 is 6. So 2 multiplied by this vector would be the same as vector v2. And notice what this vector is right here. It's the exact same thing as vector v1. And so what we have just shown here is that vector v2 is a scalar multiple of vector v1. In other words, the direction vectors for these 2 lines are scalar multiples of each other, which means they're parallel, which then in turn means that these 2 lines are also parallel. Okay, so our final answer is this. We know that vector v2 is equal to 2 times vector v1, which means that vector v1 is parallel to vector v2, which then implies that line 1 is parallel to line 2. And that is our final answer. We now know that those 2 lines have to be parallel since their direction vectors are scalar multiples. Okay? And so that's really all I had for this lesson, but if you do want to see some more examples, I have more in my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.